Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder how your feelings and actions echo back and forth throughout your day, especially when those feelings aren't so easy to pinpoint, like those subtle shifts in your mood that you can't quite explain? Well, today we're diving into a fascinating new way. Researchers are trying to map these inner emotional landscapes. This paper is all about a new tool, a computer program called ezLVAR, that helps scientists understand how our emotions and thoughts change over time and influence each other. It's like giving us a clearer map of our own internal weather systems. You know how sometimes you feel positive and then that feeling sticks around for a while, maybe even influencing your next feeling, or how a negative mood can seem to linger. Psychologists are super interested in this stuff, especially in how our emotions fluctuate throughout the day. But there is a catch. Often, the things we want to study, like happiness or sadness, aren't things we can directly measure. They're latent, meaning hidden. We try to measure them indirectly, like through questions on a survey. So researchers have to deal with two big puzzles at once. First, how do our survey questions actually measure our hidden feelings? And second, how do these feelings predict each other over time? This research introduces a clever way to tackle this called the three-step Latent Vector Autoregression method. Think of it like breaking a big, complicated problem into three simpler steps. This makes it easier to analyze and understand. The problem was, until now, there wasn't a super easy, ready-to-use computer program to do this. And that is where ezLVAR comes in. It is a new tool for the R programming language, which is free and widely used by scientists. This paper walks us through exactly how to use it, with examples. The kind of data they're talking about here is called intensive longitudinal data. Imagine asking people multiple times a day for many days how they're feeling. That's the data we're dealing with. It gives us a super detailed snapshot of how things change moment to moment. To show us how this works, the researchers use a real-life example. They looked at data from students who reported their feelings 6 times a day for 40 days. They asked about positive feelings like happy, excited, relaxed, and satisfied, and negative feelings like angry, anxious, depressed, and sad. This is what a small part of that data looks like. You can see the person's ID, the day, and then all these different question scores. Some scores are missing, which is totally normal in this kind of research. For their example, they focus specifically on positive affect, which is like our overall good mood. They wanted to see how positive affect changed from one moment to the next, and if it influenced itself later on. So let's recap this three-step latent vector autoregression idea. It's split into 3 parts. First, they estimate the measurement model. This is where they figure out how well the survey questions actually measure the hidden feelings, like positive affect. They use a common statistical method called confirmatory factor analysis for this. They use a tool called LAVAN within R for step 1. They set up the model by telling the program which questions measure which hidden feeling. For example, they said that the hidden feeling POSAF, that's positive affect, is measured by the questions happy, excited, relaxed, and satisfied. After running this, they can look at the results, like these loadings. These tell you how strongly each question is linked to the hidden feeling. They also look at residual variances, which are like the unique parts of each question's score that aren't explained by the hidden feeling. Next, in step 2, they use the results from step 1 to calculate factor scores. Think of factor scores as the best guess, or the estimated score, of someone's hidden feeling at each specific moment in time. Since these are just estimates and not the true feelings, they come with their own uncertainty, which the researchers carefully account for. This is done with the step 2 function. It takes the results from step 1 and spits out information about these factor scores, like their reliability. Reliability here means how well the factor score really represents the hidden feeling. A really cool thing about this method is that you get to see these factor scores. You can even plot them to see how someone's mood changed over the days. This is super useful for spotting patterns or weird stuff, like if someone's mood was consistently low or if it spiked unexpectedly. They also mention that in real-world data, the time between measurements isn't always the same. For example, there might be a big gap overnight. To handle this, they show how to fill in those gaps with missing values to make the time intervals more even for the analysis. Finally, in step 3, they estimate the structural model. This is where the real magic happens for understanding the dynamics. This model looks at how the hidden feelings at one time point predict the hidden feelings at the next time point. This is where we see the vector autoregression part, how a collection of variables, our different feelings, predict themselves over time. To set up step 3, they need to define 2 main matrices. The A matrix is for the regression effects. This tells us how much a feeling at one time predicts itself for other feelings at the next time. For example, how much does positive affect at time t predict positive effect at time t(1)? The Q matrix is for the innovation covariances. These are like the leftover surprises or unexplained variations between our feelings at a given time point after accounting for the previous time point. Then, they feed all this into the step 3 function to get the final results. And here are the results for their simple model of positive affect. They found a really strong autoregressive effect, meaning that positive affect at one time point strongly predicted positive affect at the next. The estimate was about 0.9, which is very high. This suggests a lot of emotional inertia in positive affect for these participants. But life isn't simple, and neither are our emotions. This package isn't just for basic models, it offers advanced options. One really important one is random intercepts. This is crucial because people have different baseline levels of emotion. Some people are naturally more positive than others. The simple model assumed everyone started at the same emotional baseline, which is unrealistic. Adding random intercepts allows the model to account for these stable, individual differences in average mood. When they added random intercepts, the autoregressive effect dropped from 0.9 to about 0.67. That makes sense. If you account for the fact that some people just start out happier, the day-to-day persistence of happiness within individuals might appear less extreme. It's a great example of how accounting for individual differences makes the findings more accurate. They also discuss multi-group modeling. This is handy if you want to compare how dynamics differ between, say, men and women or different age groups. You can set up the analysis to see if the measurement of emotions is the same across groups, and if so, whether the way emotions influence each other differs. Here, they even show how to set up a multi-group measurement model. They're telling the program about a new group variable and specifying which parts of the measurement model should be the same across groups and which should be allowed to differ. Then, they run the step 3 analysis allowing for group-specific structural model parameters. This lets them see if the autoregressive effects or innovation covariances are different between the groups. Another powerful feature is mixture modeling. This is for when you suspect there aren't just a couple of distinct groups, but rather qualitative types of people with genuinely different dynamic patterns of emotion. It is like finding hidden personality clusters in how emotions unfold. They ran a model with 2 clusters or types of people. The results showed 2 distinct patterns. One group had a lower autoregressive effect and higher unexplained variation, meaning their positive affect was more changeable and less predictable day to day. The other group had a very high autoregressive effect and low unexplained variation, indicating a very stable, persistent positive effect. This is fascinating. It suggests some people have moods that bounce back quickly, while others are more likely to stay in the mood they're in. A big challenge with mixture modeling is deciding how many of these hidden groups or clusters to choose. Too few, and you miss important differences, too many, and you are just overfitting the data. They introduce a function step 3, multi-to-run models with different numbers of clusters, and then model A selection to help compare them using criteria like A, C, and big. This summary shows the comparisons. In their example, the criteria seem to point towards a model with 4 clusters, suggesting there are indeed quite a few different ways people's positive effect unfolds over time. Now, what does this all mean? This ezLVAR package and the stepwise method it implements is a huge step forward for understanding dynamic psychological processes. It makes complex analyses much more accessible. Of course, no study is perfect. They acknowledge a few limitations. One is that the measurement model assumes the survey items are continuous, when in reality they are often ordinal. Like Likert scales, they suggest future work could use methods better suited for ordinal data or even incorporate item response theory. Another point is that VAR models usually assume measurements are taken at equal time intervals. They had to do some workarounds for the nighttime gaps. They mentioned that continuous time modeling could be a more elegant solution in the future, which models change as a continuous process rather than discrete steps. And a really exciting future direction is adding covariates. Think about explaining why someone might be in one emotional cluster versus another. If you could link cluster membership to things like personality traits or life events, that would be incredibly powerful for understanding the drivers of our emotional dynamics. What I find so compelling about this research is that it's moving us beyond just snapshots of how people are feeling at one moment to understanding the living, breathing dynamics of our inner lives. It is like getting a weather forecast for your emotions, but with the ability to see how the weather patterns themselves change and interact. The ezLVAR package sounds like an amazing tool that will let more researchers explore these complex emotional landscapes with greater ease and sophistication. It really highlights how our feelings aren't static, they're a constant dynamic dance, and now we have better tools to watch and understand that dance. What do you think about these findings? Have you ever felt like your moods have distinct types or patterns? Let me know in the comments below. If you found this breakdown helpful, please give it a thumbs up. Subscribe to RUBIN'S Mind Lab for more science deep dives, and hit that notification bell so you don't miss our next exploration into the human mind. Thanks for watching, and I'll see you in the next video.